Hi everyone, I'm Tim Kington and this is Java for Beginners. Today we're going to dig into the heart of Java, defining classes, and creating objects from them. So today I'm finally going to stop hand-waving classes and we're actually going to dig into what is a class, how do we define a class, what are they for. All of our Java programs have classes in them. The simple ones we've been writing so far mostly had just the app class that was given to us when we created the project. But in most Java programs, we're going to have many classes. Classes do many things for us. One of the things that they do is group data together. Let's say that we had a program and we wanted to keep track of some points, x, y coordinates. Maybe we were going to draw a graph or something like that. Right now, with the knowledge we have, we could define x as an int and y as an int. And then if we wanted a second point, we would have to say x2 and y2. And if we wanted a third point, we could do that again. Now, we haven't talked about arrays yet, but if you know about arrays, we could use that to help. We could have an array of our x coordinates, an array of our y coordinates, but we would still have these separate arrays that don't really go together. And it would be hard to sort of remember how the different pieces of data fit. What we'd really like to do is have an entity that represents an XY coordinate. And that's one of the things that classes let us do. So let's create a new class to represent an XY coordinate. We will call it point. Now we're actually going to look at everything that's here in our files for the first time. So we have a package statement. Classes begin with a package statement that has the name of the package they're in. This is basically the folder path where the Java file lives. In our project here, we have a source folder, source main Java folder, that holds all our source code. And then within that, we have a package called com.example. What that means is that we have folders called com, and then a folder inside of that called example that live inside of our source main Java directory. So the directory structure in the file system needs to match the structure of the packages in our Java program. If we're in a package called com.example, that means there's a folder called com that contains a folder called example, and that point.java is inside that example folder. This is how we organize our code. It has implications for visibility that we'll talk about a little bit later on. And when we want to reference classes in another Java package, we will use an import statement and we will give the name of that package. So that's what we've been doing with import java.util for the scanner and a few other things that we've run into. The imports for our JUnit asserts. When we define a class, we're pretty much always going to make it public. We'll talk about access specifiers soon. Then we say class, and then we give the class a name. In Java, our class names are typically capitalized. So we'll say point, and then we can declare member variables in our classes, which we have not seen yet. For now, I'm going to make these public, and we're just going to use our class as a way of grouping data. So we could say public int x, public int y, and this would give us an object that contains an x and a y coordinate. Now there are classes and there are objects. The class is sort of a blueprint, and the object is the house that we would build from the blueprint. So all of the houses we build from the same blueprint are going to have the same basic structure, but they might look a little different. Maybe they're different colors, they have different, trim on the insides, but the structure of the house is going to be the same if it came from the same blueprint. Likewise, our point objects are all going to have the same structure. They will all have an x and a y coordinate in them, but each one might have different values for x and y. Back in our app class, now if we wanted to keep track of 2 points, we can define points like this. We would say p equals, and when we create an object, we're going to say new and the name of the class, and then we'll put some empty parentheses for now. More about that later. And if we want a second point, we can declare it the same way. And these point objects are going to contain x and y coordinates. So we can say p.x equals 2, p.y equals 3, and we could give the values inside of point p2 different values. So p2's x is 4, and p2's y value is 7. The compiler is happy with this. We can run this code. We could try to print out some of the data, but the debugger can show us what's actually going on here. I think that's going to be more instructive. So we've created 2 point objects. If we look at our local variables over here, we'll see point at 9. Now these at and numbers here are actually the object IDs. Sometimes in debugging that's useful. But if we expand P, we can see that this point object P contains an X and a Y value. And they are the 2 values that we set here. If we expand P2, we can see that it contains an X and a Y value. X has been assigned 4. We have not yet executed this line of code, so Y is still 0. But after we go past this line, Y has the value 7. So now we can create an object that holds some data, and it keeps that data grouped together. It's much easier to talk about points in our code than it is to try to keep track of an X coordinate and a Y coordinate and remember which X's go with which Y's and so on. You may not have noticed this, but the rules for initializing objects are different from the rules for initializing local variables. When we ran our code here and we hit this breakpoint, p2.y has a value of 0. If we tried to print out the value of p2.y before we had initialized it, before we stored any data there, the virtual machine will happily print 0. So inside of objects, all of our primitive types have default values. Integer types are going to be initialized to 0, floating point types will be initialized to 0, and Booleans will be initialized to false. That is not true with local variables of primitive types. If we say something like int x here, and then we try to print it out, we'll get a compile error. That's because local variables do not have default values. So we're going to get an error here that says the local variable x may not have been initialized. Now we could get by creating objects and initializing the fields manually like this all the time, but it's kind of inconvenient. It turns out that there is a better way. We can write what is called a constructor, and it's a method that will be run whenever we create a new object of this type. So whenever we create a new point, it will call a method, and in that method we can initialize the object. We'll make it public, and this is a special method, and it doesn't need a return type. Most of the methods, basically every other method in Java needs a return type, but constructors do not. So here we have our constructor for the point class. The name of the constructor must match the name of the class. And then in this constructor, we can initialize our object. So we could initialize x and y. I guess let's give these values I haven't already used in the main method. And if we come back here and we watch what happens when we run our code, we'll see that the point will initially have those values. So if I step, we get a point object over here. When we look at it, it's got the values 0 and 1. And then as we step forward, these lines of code overwrite those values with 2 and 3. That's fine, but it's much more useful to be able to pass some of the values into the constructor to initialize our point object. So we can add parameters here just like we can with any other method. So let's add int x and int y as parameters here, and then we'll assign these to our member variables. Here we run into a bit of a problem. We want to say x equals x. We have a parameter called x, and we have a variable inside the object called x. Well, if we say x equals x, this isn't going to do anything. The compiler knows that at this point, we have two things called x. We have a local variable, which is a parameter, and we have a member variable in our class. So variables defined at the class level outside of our methods are called member variables or instance variables. And those are part of the object definition. Every object we create of this type, every point object, is going to have an integer called x in it and an integer called y in it. The compiler needs a rule to decide which x we're talking about here. And it's going to use the closest one, the one that was defined closest to where we're using it. So we're going to use this parameter whenever we just say x. That means if we say x equals x, we're copying the value from this parameter x back into the same parameter. And the compiler's warning us because this does nothing useful. If we want to access the instance variable x when we're inside of our class, we're going to say this.x. This is the name of the current object. And when we're inside a constructor, the current object is the one that we are initializing. So now we're copying the parameter x into the instance variable x, and then the parameter y into the instance variable y. If we change our constructor to take parameters like this, our old code won't compile anymore. Now when we say new point, we're going to have to supply values for the constructor. So we need to pass in an x and a y value. We could change this to be 2 and 3, and now we don't need to assign those values separately. And we can change this one to pass in 4 and 7, and now we don't need to assign those separately. And we can step through the code and see that this works. So at this point, if we step into the constructor, we'll see that there is a local variable called x that is a point. That's the point object that we are initializing right now. And the x and y values are 0 initially. We can step through the constructor and watch those values get initialized. So x is 2 and y is 3 now. And if we step again, we'll go back to our main method, and we can see that there's now a variable called p that is a point, and it holds the values 2 and 3. And if we step again, this time I won't go inside the constructor. We got another new point object. This time x is 4 and y is 7. So that's a nice way to initialize our objects. Before we wrote this constructor, we had calls here with no parameters. But these are still calls to a constructor, and we didn't write one. What's going on here? It turns out the compiler is going to supply us with a default constructor if we don't write one ourselves. So if our class just looks like this, then the compiler will put in a constructor that's basically public point with no parameters and no code in it. It doesn't initialize anything, doesn't do anything useful. I guess you could say that it initializes our member variables to their default values, so it assigns 0 to x and y. Once we've added a constructor ourselves, the compiler no longer supplies a default constructor. And now this code is an error because it's trying to call a constructor that doesn't take any parameters, and there are no constructors around like that. So now we have to add the parameters to our calls, and then our code will work again. Sometimes we will want more than one way to initialize our object. In this example, it's a little bit silly, but we can add another constructor that takes different parameters. Let's say that we wanted a way to initialize a point object with just an x coordinate. We could write a constructor like this. And now in our main method, we would be able to initialize points using the old constructor or the new one. If we pass a single value, then that would be assigned to x. If we pass two values, x and y would both be initialized. There's nothing really special about the body of a constructor. We can write any kind of normal code that we want in here. We could have if statements and other things. It's typical to just initialize the member variables to get the object ready for use. Once we've created these point objects, we can use them in our code. And we can do things like print out p.x. We can really use p.x or p.y anywhere in an expression that we would be able to use an integer variable. While we can write our classes this way and write code to use them this way, where our code reaches directly into the objects and changes values or reads them, it turns out this is a mistake. In a small program, it doesn't matter, but in a real-world application, you're going to have many classes, and things are going to get very complicated. You don't want random bits of code reaching into the innards of your object and changing values there. That's going to cause bugs, and when you make changes to your class, that's going to cause hard-to-find bugs in other parts of the application far away from where you made the change. Let's look at an example of how to avoid this. Let's create a class called student. And we'll make our student hold a name and an ID number. And we'll start out with our ID number as an int. And then we could write in our main class some code that uses our student class. And let's give our student a constructor so it's easy to initialize our name and ID. So we'll say we have a string name and an ID. These get initialized here. And then in our app class, we can create a couple of students. And Grace's ID will be 123, and student S2, new student. And we'll initialize this one 456. And this works pretty much as we'd expect it to after the previous example. So if we set a breakpoint here, we can see, no, I guess that breakpoint doesn't work because it's after the end of main. All right, so we can see that we got a student object with an ID of 123 and a name of Grace Hopper. If we step one more line, we get a second student with the other values. All right. Now we could have a bunch of code in our application that's reaching into these objects and changing the data. So let's say that we wanted to update Grace's ID and we wanted to print out the ID of the other student. And you can imagine code like this spread across our application. So we have many classes and code in all of those files using student objects and changing IDs or reading IDs or changing and reading names. And then we realize we've made a mistake. We are storing our student ID as a number, and we start issuing students IDs that contain letters as well. Well, we can fix that here. We could say, okay, the ID is a string now. That can contain numbers and letters. We'll update our constructor here. But now, all the code in our application that used this is broken. Every piece of code that's writing to the ID doesn't work anymore. There are places where we're reaching into the object and getting the ID and displaying it on the screen, and we're not doing it in the correct way because we're displaying it where we expect an integer, and it won't necessarily be an integer anymore. So we're going to have to go through the rest of our application and make a bunch of changes. This is not what you want to happen when you make a change inside a class. There is a better way. Instead of letting other classes access our data directly, we can make these member variables private. Now we've been using public in a few places so far, and I've been avoiding explaining it. Now it's time to finally say what that means. So public means that something can be seen from all other classes in your application. This constructor could be used anywhere in our application because it's public. The class student that we're creating here is public, so it could be used anywhere in our application. If something is marked as private, it can only be seen in the class where it's defined. So name and ID can be accessed inside the student class as they are here in our constructor. But back here in our app class, we now get errors when we try to access them. The field student ID is not visible. We would get the same error if we tried to access name. So it's a best practice actually to make our member variables private and then provide methods that let us access those values. So we can create a method here that will return our name. It's going to return a string. We'll call it getName, and it's going to return this .name. We can also make a setter method. We'll call it setName, and it will have a parameter called name. And we will update the name in the current object when this is called. And we can do the same thing for our ID. If we write our code like this, then when we want to get the value when we want to change the value inside the object, we would say s.setID, and then we would pass 567 in as a parameter. And when we want to print the ID from student 2, we would call getID. So this is going to have the same effect as the old code, but it's a better design. Let's see this in action. So we've created our two students, and now we're going to call s.setID. So we've seen syntax like this before. We've done in.nextInt. We've been calling methods on objects, but this is the first time where we could really talk about what was happening. So s.setID, what that means is we're going to call the setID method on the object s. That means that when we step inside this setID call, the current object is the object on which we called it, so S in this case. And that object will be called this inside the method. So if you look at the local variables when we're inside setID here, we have our parameter ID where 567 was passed in. And we also have a variable called this that points to a student object. And if we look at that student, we can see that it's the one called Grace Hopper. And back here in main, that was the student S. So when we said s.setID, that means we're setting the ID on this student object. And in here, we're going to assign the local variable ID into the object's ID. So if we step, we can see that 567 has been assigned here. So calling this method let us change the data inside the object without directly accessing that variable ID. And then the get ID is going to do the same thing. Since we called it on the object S2, it's going to, S2 will be the current object inside the call. If we step in here, you'll be able to see that the variable this points to the student called Ada Lovelace. And then we're going to return the ID from that object, 456, and that will be printed on the screen here. All right, so far this is no different from accessing the ID variable directly. So here's where we come out ahead. When we want to change the implementation of the student class, changing private details will not necessarily cause us to change the calling code. Now there are limits to this, but we can change our ID to be a string if we've decided that we should allow that. If we want the calling code to still work as much as possible, we can allow this constructor to still work, so we can pass in a string name and an integer ID, and then here we'll need to convert this int into a string so that we can store it in the string ID member variable. So to convert an int to a string, there are many ways to do this. We can say string.value of, like so. A really common idiomatic way to do this is to add an empty string to our integer. If you take the empty string plus ID, that will convert ID to a string and then add nothing to it, and it will now be a string. So this might be something you would see in real production code pretty often. So this constructor will still work now. We convert the ID to a string and we assign it. Get and set name have not changed. Set ID, we can allow this to work taking an int. We would have to do the same thing, convert that ID to a string. Get ID, we probably do have to update. So any code that was calling get ID is going to have to change because it is receiving a string now and it can't rely on ID being a number. So now in our application, we can go look at the code that's using the ID, and we'll have a few places we need to touch. Anywhere that's calling get ID and using that as a string, we may have to look at and update the code. But calls to set ID will still work, calls to our constructor will still work. And in this case, since println can print any type, it doesn't care that get ID is returning a string now instead of an int. So we didn't have to touch this line of code. If we run the program, we'll see that the result is the same. We print 456. And if we stepped through it and looked at the data inside of it, we would see that the data is working pretty much the same way, except that ID is a string now. So we have Grace Hopper with a string 567 for an ID, and Ada Lovelace with a string 456 for an ID. So we've had to make minimal changes to our program when we made the change to the implementation of student. That's a sign of good design. This concept of making our member variables private and having get and set methods for accessing them is called encapsulation, and it's one of the fundamental principles of object-oriented design. Now that we've changed our ID to be a string, this constructor is not very convenient anymore. We're going to need another constructor. For example, in our main class, we might want to create a student whose ID contains a letter. All right, this should be allowed now since ID is a string. And this won't compile because our constructor right now insists on an int. Java has a thing called overloading, which means that we can define multiple methods with the same name as long as their parameter types are different. So here we have a constructor that takes a string and an int. We can have another constructor with the same name that takes two strings. And here we would assign name and ID. When we call our constructor in main, the compiler is going to be able to figure out which one we're calling based on the types of the arguments. So here we're passing a string and an int, and so it's going to call that constructor. In fact, if we hover, we can see the prototype for that constructor. And if we hover over this one, we can see that we're calling the one that takes 2 strings. If we want this student class to be fully useful with our new ID type, we're also going to need a setID method that takes a string. So we would do something like this. And now in our main method, we would be able to change an ID to contain letters. So this, whoops, we might set the ID to 567AB. And we can run this and see that it works. So we have our student Grace Hopper, whose ID has been updated, and we can step and see that we print the right ID from Ada Lovelace. So overloading works for constructors and for normal methods. Here we have 2 constructors, which are basically methods with the same name, and they take different parameter types here. Here we have 2 methods with the same name, setID. They take different parameter types, int and string. So in our app class, the compiler can tell which one we're trying to call. When we call setID here with the string, it knows which method we are referencing. Now we've ended up with some cruft in our code here. We don't really want to keep this old student constructor around, and we'd rather not keep this old setID method around, but that's the price you pay for backward compatibility. Any program over time, its code is going to become uglier, and this is sort of an example of that happening. We can imagine that our initialization code might be longer than this. Maybe we had to do a bunch of work with the name and initialize something. So we could imagine that the part that deals with the name is, 10 or 20 lines of code. We wouldn't really want to repeat that code in both constructors. We could actually put that code in one place and call it from both of our other constructors. So let's pretend that here we had do a bunch of work with the name. So there's a bunch of code there, and then that code is repeated here. And we don't really like that. We don't want to have a bunch of code in 2 places. If there's a bug in one of them and you fix it and you don't notice that the code is repeated somewhere, you'll still have the bug come up mysteriously sometimes. In general, it's a bad idea to repeat yourself in your code. So many of the things we're going to learn are ways of eliminating duplicated code. In this case, what we can do is write a constructor that deals with just the name. So we could have a constructor here that takes the name and handles the name part of the initialization. So let's say that it does whatever this mysterious work is, and it initializes our name. And then in our other constructors, we're able to call another constructor in the same class using the keyword this. And when we do this in this way, it's terrible that they use the word this here. Python uses self, and it's a lot easier to talk about. When we are trying to call the other constructor here, we use the keyword this with a parenthesis and parameters. So since this constructor wants a string name, we're going to pass the name into that other constructor, and we can do the same thing here. If you're going to call this, it has to be the first line of your constructor. We cannot put this down here. We'll get an error. Constructor call must be the first statement. We are seeing the keyword this used in 2 different ways. It means the current object when we say this dot. And when we use this as a method name and we call it, it means we're calling another constructor in the same class. So here we're calling this constructor, and when we have arranged our code in this way, we don't have to duplicate all the code that was initializing name. Let's take a look at how this executes. So here we're calling the constructor that takes a string and an int. If I step in, you'll see that we are inside that constructor. the first line of this constructor is going to call the other constructor. So if I step in again, now I'm in here, presumably doing a bunch of work with the name. Then we're going to initialize the name. I forgot to say that the default type for object types is null. Up until this point, we've been thinking of strings as primitives, and they're really not. So strings are initialized to null when we create an object containing a string. So name is now Grace Hopper. If we step again, we'll come back to this constructor and continue after the method call. So now we're going to initialize the ID, step, and now ID has been initialized. So you can see ID and Grace Hopper have been stored correctly. And then we'll go back to the main method where we were called. And if we step into this constructor, which is the other one that takes two strings, then we will call the other constructor, initialize the name, come back to here, initialize the ID, and return. So this is a thing that comes up once in a while. It's not super common that you need it, but constructors can use other constructors as part of their initialization. I think that's enough for now. We've gotten to see a bunch of new stuff about classes and methods and constructors, and we'll come back next time and we'll look at other types of methods in our classes, and we'll talk about assignment and how memory really works when we're dealing with objects. Well, that was a lot of new material. We still have more to discuss when it comes to defining classes, but we'll save that for next time. Today we talked about defining classes, adding member variables to them, writing constructors, encapsulation, and how we can create objects in our main method. Next time, we'll talk about the memory model with object types. We'll talk about static, and we'll look at methods in our classes that are not getters and setters. See you then. Don't forget to like and subscribe.